Hello Capstone students, this is Dr. P, and this is a video about how to prove the SAS triangle congruence theorem using the transformation idea of congruence. Now, before I get started, I should mention that I am recording this on an app on my tablet, and I'm mentioning this because some of you, when you become teachers, might find this to be a useful tool. This is called the Explain Everything app. I have an Android tablet. It's a Samsung Galaxy Tab something, or it's not Galaxy Note. Galaxy Note is the one that blows up and doesn't exist anymore. But I'm on a Samsung Galaxy Tab tablet and using the Explain Everything app, which lets you take screencasts and records your voice and everything. So you might find that to be an interesting tool to play around with. Anyway, I'm going to use it to create a video about how to prove the SAS triangle congruence theorem using transformations. And I'm hoping this will help with one of your homework problems this week. Because the type of reasoning that we use in this proof is a little bit different from what you may be used to if you encountered proofs in high school geometry. So first, let's begin by stating the theorem that we're going to prove. So the theorem is this. This is the SAS triangle congruence theorem. Now, one thing you'll notice is that I'm being super pedantic about always saying triangle congruence rather than just SAS congruence. Because as you discovered during the presentation last time, side angle side it's certainly enough to establish congruence of triangles, but it may not be enough to establish congruence of other types of objects. So I always say triangle congruence for that reason. Now, when I write down a statement of this theorem, I'm going to write it down in terms of actual geometric objects. Any other way of writing it, like you say, oh, if two triangles have a side, an angle, and a side in common, then they're congruent, that's too vague. First of all, the triangles probably don't actually have sides and angles in common. They have sides and angles of equal measure. But anyway, let's get to the statement here. All right, so assume triangles ABC and DEF have AB equals DE. Again, I'm going to mark that in my picture by marking those sides congruent, and then measure of angle A equals measure of angle D. So I'm going to mark those angles congruent. There we go. And AC has the same measure as side DF, the same length. So I'm going to mark those as having the same length. Then triangle ABC is congruent to triangle DEF. And you'll notice when I write that, I'm writing that in such a way that the vertices are written in corresponding order. That is, use my little pointer tool here, A corresponds to D, so A corresponds to D in this congruence, B corresponds to E, and C corresponds to F. All right. When I write a congruence statement, I should always write the congruence statement that way, so that the vertices are written in corresponding order. Okay, now one more note about language. I realize I'm stacking on a bunch of little technical details, but some of you are going to be teaching this stuff, and I want you to be able to speak about it in a way that's technically correct. So when I wrote AB equals DE, you'll notice I didn't put little segment symbols over these or anything like that. That's because this statement is saying that those two sides have the same length. So the distance from A to B is the same as the distance from D to E. Similarly, I don't say that the angles angle A and angle D are equal. I say that their measures are equal. Okay. You can also say that the sides are congruent. You could actually mark these as sides and then put a little congruent symbol here, and then mark the angles congruent and then leave off the measures. But you shouldn't say that angle A equals angle D or that side AB equals side DE. You should either talk about measures or talk about the geometric objects being congruent. Okay. Anyway, so let's get on to proving this theorem here. Now, I think I am going to go ahead and just eliminate this statement of the theorem from the screen so that we will have room to work here. So I'm going to see if I can do that. Let's see, I can't do that without getting rid of all of the side and angle markings, so I'll have to eliminate everything. Oh, that's odd. Okay, I can't do that without eliminating everything. I still don't know how to explain everything groups objects that are written on the screen. It's kind of a pain. So anyway, we assumed that AB is congruent to DE, assume that AC is congruent to DF, and assume that angle A has the same measure as angle D. And from this, we're going to prove that these two triangles are congruent. So we know that three pairs of objects are congruent. Now we're going to prove that these entire geometric objects are congruent. So here's how we're going to do it. We're going to prove this using the one way I have of proving two objects are congruent. And that is, let me zoom out a bit here. So when we're starting out with this subject, the one way of proving congruence is to use the definition of congruence. Show that a sequence of rigid motions maps triangle ABC onto triangle DEF in that correspondence. Okay, and not just any sequence. I get to pick whichever sequence I want, and that's good because not just any sequence of rigid motions will do it. It'll take a specific one. Okay, so that's going to be the strategy. So now let's begin. So in class, you worked on an activity where you came up with the most efficient way of mapping one triangle onto another one. Now here, because this is a proof and I want the reasoning to generalize a bit, I'm going to do this in a way that's not efficient. I'm going to do that on purpose. Instead, I'm going to do this in several steps. The first step I'm going to do, I think I'm going to have to get rid of this if I want to do that. First thing I'm going to do is I'm going to draw a vector from A to D. So let me see if I can do that. Drawing dotted lines and explain everything is kind of a bear. Really drawing any dotted line on a tablet is difficult, but that's not bad. Okay, so that's the vector A, D. So the first thing I'm going to do is I'm going to translate triangle ABC along the vector from A to D. That's the vector symbol, to obtain a new triangle, A prime, B prime, C prime. So that's going to look like this. And I'm going to draw this as accurately as I can. Let's see, a little bit closer to vertical there, I think. Not bad. So that's going to be A prime, B prime, C prime. And you'll notice that A prime is the same as D prime. So we know A prime equals D because we translated A along the vector from A to D. So by definition, that translation takes A over to D. That's why A prime is the same point as D. All right? So that's the first step. Now the next step I'm going to do is, it looks like these two triangles, the one I just drew here, A prime, B prime, C prime, and DEF, it looks like they're just off by rotation. So what I'm going to do is I'm going to rotate that entire triangle there, that new one, by, let's use a different color here, by this angle here, that directed angle. So now I'm going to rotate triangle A prime, B prime, C prime about point A prime, which is the same as D, through the angle C prime, D, F. Just kind of like what we did in class, except now I think we're going to get a cleaner proof out of it. All right, and that's going to give me a new triangle, A double prime, B double prime, C double prime. Okay, so what do I know is going to happen if I do that? If I do that, then I certainly know that this side here is going to fall exactly onto that side, because I'm rotating it through the angle that would cause this to do that. So I know that at least this ray here, the ray from D through C prime, is going to end up on this ray. So, see if I can get this with the picture still in the frame here. Okay, there we go. All right, so we know that A double prime, C double prime, that ray is going to lie exactly on the ray from D through F. Okay, so in terms of the picture, what's going on is that this ray here, ray from D through C prime, that's going to get mapped up onto this ray here. Now I can actually say something more than that. I believe that the point C prime is going to land upon the point F. Those are going to be exactly the same. But now, why is that the case? And in fact, I claim that C double prime is going to be equal to F. And this is because that line segment, DC prime, that had the same length as the segment from A to C, because I just mapped everything over. Mapping everything over is not going to change the length of this. So DC prime has the same length as this. And therefore that has the same length as DF by our assumption, because we knew that AC and DF have the same length. So this is because that image that I just created, that A double prime, C double prime, that has the same length as DC prime, because I'm just rotating this in order to get this. And that DC prime is just a translate of AC. And because the translate, it has the same length. And we know that from the assumptions given in the problem that AC is equal to DF. This is by our assumption. All right. So in summary, we know that A double prime, C double prime. By the way, A double prime is still here. It's the same point as A prime, which is the same as D. And I know that that point C prime is going to get mapped up somewhere onto here. Now I know it's going to get mapped exactly to point F. But I want you to notice that the reasoning that I used here, the reasoning I used included a couple of components here. One was that I used this angle here to rotate this segment here onto this line. But in addition to that, I used the fact that this segment here has the same length as this segment here. So I know that this endpoint is going to move exactly up to this endpoint. It's not going to go any longer or any shorter. So to do that, I had to use the fact that these segments here, these sides, had the same length. All right. So now, once I've done that, I'm hoping that the picture looks like this. I'm hoping that the final rotation I've done is going to cause my picture to look exactly like this. Those should be on top of each other, but you get the idea. That's what I'm hoping for. But I need to show that that's actually going to happen. And that's the theme with a lot of these congruence proofs, is if you're using transformations, you actually need to demonstrate that objects are going to go where you say they're going to go. That's why I'm doing all this work here, is I can't just come out and claim that the image of this point C prime, that this is going to land exactly on top of F. I have to use some of the geometry of this problem in order to prove that. Without that, I have no way of knowing that this point isn't going to map somewhere short of F or somewhere beyond F on this line. Okay, so we need to make sure we're using all the assumptions in the problem that we're given here. Okay, anyway, let's see, what's the best strategy for getting all this onto one page? I realize I'm sort of progressively making things smaller here. But anyway, all right, so at this point, now I claim that the other vertex that I get from the rotation, B double prime, that lies on E. All right, now how am I going to show that? So I'm trying to show that this point here is going to get rotated to E. Now, why would that be the case? Well, to show this, so first of all, we know that the angle, measure of angle, B prime, A prime, C prime, that's equal to the measure of angle BAC, which by our assumptions was equal to the measure of angle EDF. That was given in the problem. At the time, we just called it measure of angle A and measure of angle D. Now I'm using extended names because there's just so much happening in this picture here. Okay, so we know that that's true. So what does that tell us? That tells us that if I have mapped this segment onto this segment, so the thing I'm trying to figure out is where does this segment end up going under that rotation? I'm hoping it's going to go exactly here. But why would that be the case? Well, that's the case because I know that this segment mapped exactly onto this, and then the angle from this segment to this other side is the same as the angle from this segment to this other side. Those have the same measure. So I know that this segment here, it at least has to end up on this ray. So the side, what was it, A double prime, B double prime, must land on the ray from D to E, from D through E, okay? So I know that at least that rotation there is going to move this side here, side A prime, B prime, somewhere out here, out this way. I just need to verify that point B prime is going to move to point E exactly after that rotation. Well, why would that be true? How do I know that point B after the rotation doesn't end up someplace further out or someplace closer in? What assumption do I have in the problem that would tell me that that's not going to be an issue? There's one more assumption I haven't used yet, and that is that we also know that A double prime, B double prime, that length is going to equal A prime, B prime, which is equal to the length AB, which by assumption was equal to the length DE. In other words, I'm using the fact that this length here is equal to this length here. And so that image, B double prime, is going to be exactly on top of E. It can't be any further out or closer in. All right. So what do we know? All right, now this is getting kind of ridiculous with the resizing of the text, but I'm trying to get everything on one page here. But I think I'm just about done. So now I know this translation rotation combo, it maps A to D, B to E, and C to F, and thus maps triangle ABC to triangle DEF. And therefore, triangle ABC is congruent to triangle DEF. And then I think we are done. So now we've shown that under the assumption that we have those 3 bits of information, the 2 sides being congruent, these other 2 sides being congruent, and these angles being congruent, we can use that information to show that the entire triangles are congruent. That is, one maps onto the other by rigid motions. Now, a couple of things I want to mention about this proof, just for perspective here. One of them is that it's not a guarantee that this particular sequence of transformations would have always worked. I've made it to be fairly general, but it's not totally general. So let me just come over here and draw an example real quick. I'm just going to hand draw this one. Suppose I gave you this triangle. There we go. And this triangle. Now that's actually not very convincingly drawn there. Let me try that again. That's a bit better. Okay, so let's say I tell you that this side is congruent to this side, this angle is congruent to this angle, and this side is congruent to this side. Could we use rigid motions to map this triangle, the one on the left, to the one on the right? Could we do that? And we could, but there's no way a translation and rotation is going to do it, right? Because a translation and rotation, both of those transformations are going to preserve the handedness of this triangle. One thing I sometimes like to do is put a symbol here, like a marking. Put a marking to mark that as my triangle. That's a P there. And then that would correspond to this, but the P would be in the other direction here. So all of the translations and rotations in the world are going to preserve the handedness of that P. They're not going to map this P onto a backwards P. We're going to need a reflection here. So when I demonstrate this proof here, there's really an addendum that's needed, which is that somewhere I might say that at some point a reflection may be needed. And the reason for that, the way that sort of comes up in the reasoning, is that it's possible under some circumstances that I might do the mapping, the translation and the rotation, and wind up with this triangle instead. Something like that. And then have to reflect across the line DF. Okay, so that's a possibility that might occur. It didn't occur here, and I wrote the proof without it, but it's something you got to be mindful of. And then this is really the major thing, even more major than this whole issue over here, is the issue of just how we write these arguments. Number one, I really tried not to claim that anything goes to anything. Like I didn't claim that any point maps onto any other point without giving some reason why that was true, right? For example, when we rotated the point C prime, and we rotated this whole side onto this side, well, we could do that just because we can always choose this angle here for the rotation. But once I did that, I had to prove that C prime lands exactly on F, that it doesn't go any further out or any closer in towards the point D. And the key to that was just understanding that this segment here has the same length as this one. That was one thing. And then the other thing was, in order to do that, I had to use all the assumptions given in the problem. You'll recall I was given three things, that these were congruent, and these angles were congruent, and that these angles were congruent, or sorry, these sides were congruent. And I used all three of those facts in some very well-defined way at some point. If I see a proof that you've written and it doesn't use all the given information, that doesn't sink the proof. Maybe you don't need the information, but if the information is needed for the theorem to be true and you don't use it, then you can't possibly have a valid argument because you've proven something broader than what's actually true. Okay, anyway, I think I've talked this one just about to death. I promise when I make these videos, I don't usually make them this long, but this is kind of a complicated topic and I wanted to make sure and treat it thoroughly. So anyway, best of luck with the homework. You have a slightly different problem to work on, which is ASA triangle congruence. And I think I've included some supports there. So please let me know if you have any questions. Anyway, see you in class.